Welcome everyone. I am Rati Ludhani, pursuing PhD at Indian Institute of Technology, Bombay, at Department of Mathematics. I am a PMRF fellow here. We are going to discuss sample questions related to lectures 14, 15 and 16. Feel free to ask if you have any doubt. Okay, let's start. Let H be a ring of all positive Cauchy sequences under addition and multiplication. So I have just written it down what are Cauchy sequences for the reference. Okay, so first let's see what are Cauchy sequences. The sequence is like this. I'll change color. Where an belongs to rational number is a Cauchy sequence if for every epsilon. So we are in right now we are in rational numbers, let's say, or we could say in general also. Okay, it is not mentioned here, so let's do that. Is a Cauchy sequence if for every epsilon greater than 0 there exists n belongs to n such that for all m greater than 0, am plus n minus an less than or is less than or equal to epsilon. So basically, the sequence should the numbers in the sequence will get close to it, and that's why it will kind of converging to a number. So these are Cauchy sequences, and actually this set gives the real number set and gives a precise definition for real number, and this was given by Cauchy. So the name for the sequence. Okay, so let H be a ring of all possible Cauchy sequences. So H is given to be the ring of okay, so under addition. So this is H. Okay, I'll just write an n greater than 0, and let's say an let's keep it in the rational number set. An belongs to Q, and this is under addition, and addition and multiplication has been defined like this. And if you open the lecture notes, you'll understand why this has been defined, and this is well defined notation, an plus bn. So we'll just add the sequences, so which will be kind of component wise, and the product is similarly just multiplying all the elements at each places. So, and yeah, so this is your H. Now J is considered to be the set of sequences n greater than or equal to 0 such that limit n tends to infinity, an is equal to 0. Okay, so yeah, so what is limit okay, we can have the definition of limit, which is equal to so okay, just for completeness, let's write limit n tends to infinity, an is equal to a if and only if for every epsilon greater than 0 there exists n belongs to n such that a n plus whatever you have minus a is less than or equal to epsilon, and this is true for every m belongs to n. So basically it should converge to an element that is a. So here also it just says it will become the difference between any two elements after a certain step is very less. So this is that's why it converges. And yeah, so the definition of limit is exactly this. I hope you are aware of it. Okay, So this is your, and J is saying you take all the sequences which converges to 0. So it's like if you take 1, 1 by 2, 1 by 3, so it will converge to a number that is 0, which you can easily prove. And so this is like that. Now what has been asked, which one of the following is true? A real number has a unique Cauchy sequence in H. So we are in real number, so it's fine to define for rational numbers. Rational means an is from rational number. A real number has a unique Cauchy sequence in H. J is not a maximal ideal of H. So, okay. First, let's see. A real number has a unique Cauchy sequences in H. So, what does that mean? It means they want to ask, can you can there be like just take any real number R? Will you get only one sequence which converges to R in H, in your set H? What do you think? Can you find any two sequences which converges to R? So just take, for example, just take R, comma R, comma R, comma R. So this converges to R, no doubt, because all the elements are R. So it's like just take here R minus R. So whatever epsilon you choose, it will, and as epsilon is greater than 0, it will always be 0. So this is 0. So this sequence converges to R. And let's take R plus 1 by 2, or maybe let's start with 1, or maybe you can do it like this. Let's take R plus 1, R plus 1 by 2, R plus 1 by 3, and so on. So what you are taking, this is an is your, okay, it looks messy. So an is your R plus 1 by n. So if you take this sequence, then it will converge to R because 1 by n converges to 0. Is that clear?
Yes.
Okay. So this will also be converging to R. So we have two sequences which converges to R. So for any real number, you can take these. You just take any real number, you will get these, and many more. You can take 1 by 2 and like anything you can take. So what is going on here? You just take some sequence. Let's say just R, and later you just take R plus something which converges to 0. So that will always help. So because because of this property, it holds. So definitely first is not correct. Second, J is not a maximal ideal of H. So let's see if okay, and I can do scrolling vertical. Yes. So second, J is not a maximal ideal of H. So this is also in your notes. J is not a maximal ideal of H. So is that clear from the notes, or should I explain? Have you, yeah.
Explain.
Okay. So J is not a maximal ideal of H. So that is not true actually. It is a maximal ideal, and J is what? J is your, okay, we have the definition here already. So let's see. Okay, so we need to prove that this is a maximal ideal. So so what should happen from the definition of maximal ideal? There must be no so let's say there should be no let's say J dash such that which is a ideal and which is properly containing J, and it is properly contained in R. So and this is your H. So R is your ring, so here it is H, so I'm writing H. So that is the definition. You should not be able to find such a J dash. Okay, so that means if you have J, you put something here, you put something outside J. If you have something H minus J, just put something, let's say Bn sequence. Then so J union Bn sequence, if you take this as a set, okay, this is the notation for sequence. So J union Bn should be equal to, when you take this and when you kind of generate it, you will get the whole ring H. So that is the definition for maximal ideal. Okay, if you want to prove that this is a maximal ideal, so you consider any outside Bn, and when you take it in J, so when you take the ideal which has J and Bn, then you get the whole ring. Okay, so let's see if this is true or not. So to show basically proof for this claim, so as we said, let Bn n greater than 0 belongs to H but not in J. Okay, so this is outside J. What does that mean? It should converge to some number which is non-zero, because J contains all the sequences which are converging to 0, right? So Bn is something, this implies Bn converges to some B which is not equal to 0, right? Yeah, right. So Bn converges to B which is non-zero. Now okay, so what we need to find out, so if you can if you ever want to prove that this is the whole ring, like if you combine J with Bn, then you get the whole ring. That means you should be able to find out the unity, multiplicative identity, which is what? If you take all the ones, that is your multiplicative identity here from the definition itself. Because here if you take 1 into so if you take 1 for Bn, then you will just get An. So this is your multiplicative identity in this set. So you should be able to get this identity. If yes, then you are done. Okay, so let's see if we can have using Bn and using J. So this is the ideal generated by Bn and J. Okay, so how shall I start? Okay, so okay, we'll prove that so Bn is what? Bn is B1, B2, this is your sequence, right? So maybe sequence we can write it in this form, B1, B2 up to and so on. Okay, and this converges to B, so there is a well-known result, or maybe let's say claim, 1 by Bn converges to 1 by B. Okay, so so basically what do you have? You have Bn minus B is less than epsilon. So let's, for every epsilon greater than 0, there exists some n belongs to n such that 1 by Bn minus or maybe this by 1 by n is less than epsilon. Okay, so I'll just change it to B if you remember, such that this for all m greater than or equal to maybe 0 or not, that's okay, that is not a big deal. You can always take n plus 1. Okay, so this should happen there for every epsilon. You should be able to get that this n such that this happens. Firstly, this claim is only true when B is not equal to 0. So because otherwise 1 by B is not defined, right? So for example, if you want to have such an example, let's take 1 by 2, 1 by 3. Okay, this converges to where? This converges to 0. And if you take the inverse of every element, you will get like this, and definitely this is not convergent, not convergent. So this statement definitely not valid when b is equal to 0. So b is not equal to 0, then we can get it. Okay, so here you have 1 by b n plus m. So you need to, so let's take, let epsilon, should I start with epsilon? Let epsilon greater than 0. Okay, then what will happen? You know that okay, let epsilon greater than 0. Usually we get back to this. Okay, what I am doing. Okay, let's start with this and then we'll get that there. So for every epsilon, you know, this implies there exists some n belongs to n such that since bn converges to b, there this implies there exists n belongs to n such that bn plus m minus b is less than epsilon, right? Is that okay from the definition?
Yes.
Now you take n, and this is true for every m. Okay, for every m belongs to n. Okay, so after a step it will the difference will get very low. Okay, so from this what can you write? Okay, so you can write like this. Here you can write this again. Okay, and now we need to go to this. Okay, sorry, this will change, as you know, when you so when you take the inverse, it will, the equalities will get changed. Okay, and right, just assume these are not 0. So epsilon is something such that minus epsilon plus b is not equal to 0, just for the sake of just assume for now. So minus epsilon plus b is not equal to 0 and epsilon plus b is not equal to 0. Okay, so here what will you get? So where you need to go, that is the point. If you take this, here you will get b plus epsilon minus b into b minus epsilon. Okay, b minus epsilon minus b upon epsilon plus b into b. So you will get here epsilon b into b minus epsilon, and here you get minus epsilon plus b into b. Okay, just add one more page. So the main thing is, if you see, these are constants for a fixed epsilon. These are constants, and that will make it low. That is the point. Whenever you get something like that, then you are done. Okay, but let's see what do we have here. Okay, how shall I say? Just consider this. Sorry. For now, and if you say this is epsilon dash, this is your new epsilon, let's say, then you got some epsilon such that sorry, not so basically we always trace back and so basically find out the value of epsilon dash from here. Have you ever done this? Like, have you ever done such kind of steps? Okay, I hope not then. Sorry, this is minus, this is b square epsilon dash, and what we were trying to get the value of epsilon. So here epsilon, and you will get b square epsilon dash upon 1 plus b epsilon dash. Okay, something like that. So you get this. And now what I want to say, you start with the okay. So, yeah, so you start with epsilon dash. Let epsilon dash greater than 0. Okay, then what will happen? For such an epsilon dash, you will for such an epsilon dash, you need to find out the value of you need to find out such a thing, right? You need to find out such a n such that this happens. Then for b square epsilon dash 1 plus b epsilon dash, take this is your sum epsilon belongs to n which is greater than 0. Okay, you start with epsilon dash, that is your main, and then for such a value, this is again an integer, again a real number which is greater than 0, and this will make it what will happen with this. Because of this, epsilon dash is greater than 0, b is something okay, we don't know if it is positive or negative, it's just definitely non-zero. So you can have such that this is non-zero, and for b square this value is equal to epsilon. If you take this value, this is just notate it to be epsilon. If you take this value for such a value greater than 0, we have bn minus b is less than epsilon, right? So just for this epsilon, you have something n. Okay, there exists some n belongs to n such that bn plus m minus b is less than epsilon. Now if you go with this process, what you will get 1 by bn plus n plus m minus 1 by b is less than epsilon dash, because we find out this value from this from here only. Okay, so because of this you will get less than epsilon dash. Okay, because of this, and why you can do that? Because 1 by b is defined. Okay, b is non-zero, so because of this you will get for such an epsilon dash you get some such n such that this happens, and because of this 1 by bn converges to 1 by b. I'll write it properly in the notes, you can check it there. So this is the logics. Okay, is that okay? Have you understood?
Yes.
Okay, great. So yeah, where were we? Right. So we have 1 by bn converges to 1 by b. Okay, this is now. Now what can you do? So basically you have the inverse now. So okay. What I need to do, bn converges to b, we have this, and 1 by bn converges to 1 by b. We need the product, right? So we need 1 comma 1 1 1, this sequence inner thing. Okay, inner situation, we need this. So how will you get it? Okay, how shall I say? Okay, so 1 by bn yeah, just take the product of these two sequences, right? Just take the product of these two. So you have bn in your sequence, right? You have bn, that is the new one, and now this is an ideal, so you can multiply with any of the other thing, and now what will you get? You will just get 1, right? And that is your sequence, and that is what we need, right?
Yes.
Okay. So you have the sequence. Now what is the next thing? Yeah, so J is actually a maximal ideal, right? This is true. A real number has a unique representation is H in H mod J. So that is the actual unique way to define real numbers. So let's see if this is true. So what you need? So that is your C part. H mod J has unique representation for every real number. Okay, that is your question. So let's say you have some R and there are two sequences which converges to R. Okay, and these are in H mod Z. What does that mean? This has been defined like this. Okay, this converges to uh, okay, a real number, and like this. And you have sorry, better you write it like this. Sorry, that is not the way, because this is an element of H. Now this is the notation for any element in quotient group, right? This converges to definitely R plus J, or maybe let's say R. Okay, and here you have Bn plus J, which converges to R. So unique representation for every element. Now just take the, now we need to prove that An and Bn are same. So how will you prove that? You just take the difference of these two elements. What will you get? An, now from the definition, this will be just An minus Bn plus J. So these are the quotients. So if you remember, you are just taking the subtraction of these two, and this will be just plus J. So now this converges to R, this converges to R. So the total will converge to converges to 0 plus J, converges to 0 plus J. Now you know this is what? So what do you get? An. So this subtraction, you get this is equal to J, because this converges to 0. One more page. Yeah. So An minus Bn plus J converges to where? 0 plus J. That is what? That is just J, right? Because okay, how shall I say, like this? No, sorry. So this converges, okay, let's say this converges to 0, because An minus Bn converges to 0. This implies what? An minus Bn belongs to J, because it converges to okay, yeah, that is a way to write. So An converges to R, Bn converges to R. Actually we are in quotient group again. So and then An minus Bn converges to 0. This implies An minus Bn, this sequence belongs to J. And what does that mean? Belongs to J. And now that is your 0, because in the quotient group H mod J, that is your 0. What does that mean? An minus Bn, which is plus J, is equal to J, and or maybe belongs to J, both are fine. And this is equal to An plus, not belongs to J, sorry, this minus Bn plus J, right? So what does that mean? This is your additive identity. And this implies when you subtract the two things and when you get additive identity, that means those are same, because this minus means inverse of that. So that means An plus J is equal to Bn plus J. Okay, so this is in the quotient ring. So that's why in your every element has a unique representation. Is that okay?
Yes.
Okay. What about the fourth part? Okay. J is a principal ideal. that is something which we can never hope for here, at least. So J is a principal ideal. Can you think of like that? So what does that mean? You should be able to find out a sequence, like you should be able to find out a sequence which generates all the sequences which converges to 0. So there should exist some an such that an, when you take an, it generates the whole j. uh, Now just think of, can you find something? Actually no, because you can try it with the rational numbers. So for example, you have 3, 3.1, so like this. Sorry, not 3. I started with pi, but let's because we need to take the convergence to something which is like, let's say this. Okay, maybe. Okay, 0 point. Okay, maybe by dividing. So 1 by 10, 1 by 101, 1 by 1010, 1 by 101, 0. So when you construct a irrational number, kind of that, so this will converge to 0, no doubt. You take any other 1 by 2, 1 by 3, 1 by 4, these all converge to 0. So can you find a one sequence such that which converges to 0? No, because you can you pick something? If you can, just try it out. But because we have irrational sequences to not irrational sequence, these are rational numbers. Irrational sequences means which converges to irrational number, and that could be anything, that could be any way. So there are many sequences like that. So you have not particular any element which can generate whole all the sequences of such kind. Just try it out as an exercise. If you can actually prove this, then maybe not a particular sequence. Which converges to 0. Maybe there does not exist any particular sequence such that which converges to 0, such that j is generated by that element. Okay, that's any particular sequence an. Okay, you just try some irrational, just pick, let's say you have an. Okay, let's say you have this, and then try to have a new sequence, or maybe just take two sequence, and you think of, you cannot get it from any of them. Like you have to have those two sequences in your j to generate it. Okay, in your generating set. Okay, just try it out. If not, we can always discuss. Okay, yeah, it's a good exercise to do that. Let f be a field of order 4 raised to power n, where n is a positive integer. Then which one of the following is true? Okay, so let's see. So okay, so basically characteristic we have discussed in the last class. What? So for a field f is a field. Characteristic is a number. So what is characteristic? Characteristic of f? A positive integer n such that 1 plus 1 n times is equal to 0. And if such n does not exist, then then characteristic of f is equal to 0. So this is your characteristic. If you can find, if you sum it up like sum 1 n times, that if you get 0, and if you have okay, not smallest positive integer. Okay, this is the smallest. So if you have yeah, so you can get bigger than that. If you add 2n times, then you will again get 0. So we need to choose some small number. Smallest makes sense here. Okay, so smallest positive integer such that this happens, or if does not exist, then this is 0. For example, in integers, in the ring of integers, if you add 1 1 1, you will never get 0, right? So this implies characteristic of z is 0. And so if you have, for example, zp, let's say z5, then and these are with mod 5 definitely. So when you add 5 times, you get 0. So characteristic of z5 is 5. And you can see, if you take just 2, you will never get. So if you take lesser than 5, you will never get 0. So lesser than 5 and at least 1, because this is a positive integer. Okay, so yeah, the characteristic of if you take any prime, so there's a characteristic of zp will that is just p is a prime. Okay, this is your z. Okay, let's see. Now what has been asked, f is your field. So what they have asked, f is a field of order 4 raised to power n. So you have 4 raised to power n elements in your, and n is a positive integer. Which one of the following is true? So characteristic of f is what? Okay, so there is a okay, so okay, so characteristic of f. So if the field is finite, field is finite, then definitely characteristic is finite. If field is finite, then characteristic of f is definitely finite. Why? Because you have 1 plus 1 plus 1 plus 1. You are adding up to, and you will get something next. You will never get 0. Okay, because sorry, what I want to say, if you are saying characteristic of f is 0, sorry, is not 0. Okay, my point is this. Okay, not 0. So if field is finite, then characteristic f is not going to 0, because you have 1 plus 1 plus 1 plus 1, and if it stops, so okay, so I am saying these are all the different elements. Okay, if characteristic of f is equal to 0, then you will never get 0 when you add 1. Okay, that means, and I'm saying these are all different elements. They will be different elements when you go on. And why? Because for example, you have n into 1 and m into 1, and for example, without loss of generality, let's say n is greater than m, then n minus m into 1 is equal to 0. That means you have 0, and if n is strictly greater than m, then this value is not equal to 0. That means you have something. When you multiply 1, means you are just adding it n minus m times. Okay, and if it is non-zero, this n minus m is non-zero and you are getting 0, that means characteristic is non-zero. You have that value, at least n minus like characteristic of f is less than or equal to n minus m, because you could get lesser value also. So that means you are not getting something equal also. This is not possible that this element is equal to this element. Never going to happen. Okay, these are not equal if characteristic of f is 0. So you have infinite elements at least. So you have 1, 1 plus 1. Whenever you get, you are getting different values. So 1, 2 into 1, 3 into 1. This is the representation for 1 plus 1. This is a representation of 1 plus 1 plus 1, right? So you get all different elements. And this is going till infinite times. So field has to be infinite. The elements in field should be infinite. So if field is finite, so this is a very important thing to remember, that if field is finite, that characteristic of f is not non-zero. Okay. Now we are also saying there is one more claim. So there is characteristic of f is either a prime number or 0. Okay, so 0, now here f is finite. F is given to be what? The elements of f are 4 raised to power n, right? So this is basically 2 raised to power 2n. That is finite. Here f is finite, so characteristic of f should be a prime number. Okay, we need to prove that. So why is it a prime number? Proof of claim 2. Proof of claim. Okay, let's see if this is true. So characteristic of f is a prime number. So if not, that means characteristic of f is a number. Let's say that is not n. Let's say this is capital N, which is equal to m1 into m2. Okay, so if this is not non-prime, that means this is not equal to 1, this is not equal to 1. You should be able to write it in the multiplication. There should be a divisor other than 1. Okay, and not equal to 1, right? So you should be able to write it like this. Now you know n into 1 is equal to 0, because characteristic of f is n. That means m1 into m2 into 1 is equal to 0. That means what you have, basically m1 into 1 into m2 into 1 is equal to 0. That means you have so this is equal. And now what does that mean? Now you are in a field, and field is always an integral domain. That can be checked very easily. Okay, field is always an integral domain. So this implies either m1 into 1 is equal to 0 or m2 into 1 is equal to 0. So that means this implies n is not a smallest number. Such that n into 1 is equal to 0. This implies characteristic of f is not equal to n. Contradiction, right? So n should be prime. Is that okay? Is that okay?
Yes.
Now, very good. So field is given to be what? What? Sorry. Yeah. So a field is given to be of 2 raised to power 2n. This is your field. And now characteristic is something. Okay. So from the options, what can you see? P that divides n, 4 raised to power n, 4, 2. So only the prime number is given to be 2. So characteristic of f is equal to 2. Okay. So this should be 2. From the options, the prime number should be your answer. And
in options, if we get the characteristic of f is equal to 3.
Sorry?
In options, if we get the characteristic of f is equal to 3, 2 and 3.
In which question?
Second question.
uh, I didn't get it. So which one you are saying?
Suppose if another option there means
Oh,
characteristic.
acha, you are saying, okay, if characteristic of f is given to be 3. Okay. So actually this is the number which divides order of field. Okay. So how shall I say? Right. Okay. Mm, okay. So what is, okay, 1 plus 1 plus 1. So if you see, field is what? Field is, f is a field. This implies what? F is commutative group, right? Under addition. Under addition, it is always a commutative group. Now this is a commutative group. That means this implies order of, just think of f as a commutative group under addition right now. Okay, forget about field. Order of any element in f. Okay, order in the sense of group under addition. Okay, order of any element in f should divide by Lagrange's theorem. What should happen? Should divide the order of group. That is what? That is equal to cardinality of f. Is that okay? So if you take the set generated by 1, which is what? 1 1 plus 1 1 plus 1 plus 1 plus 1. This is your set. This is the generated by 1 in addition. Okay, so in additive group. Okay, in addition. Okay, so order of 1, so order of, okay, yeah, forget about this set is not a requirement. So it's just order of 1 should divide order of f, and that is exactly what? That is exactly the set 1. Oh, sorry, not 1. So what you are doing, you are finding some n such that n into 1, that means 1 plus 1 square in addition is what? 1 plus 1, no? So it's like this, when you take it n times and then you get the identity. So when you get the identity, that is your order, right? That is additive identity. And so this number, this n should divide order of f, and that is what? That is your characteristic of f. So this should divide order of the group. So here order of f is equal to 2 raised to power 2n. This implies characteristic of f should divide order of f. So the only option, and it is prime. So what is the option now?
2.
2? Yeah. And it is prime. This implies characteristic of f is 2. Exactly. Very good. Thanks for asking. Like, otherwise I would have missed that point. Okay. So let's go to the next question. So this was the, so 2 is the answer. Which one of the following is not a Cauchy sequence? So you need to figure out which one is not a Cauchy sequence. Can you tell me anyone from these options?
First option.
First option. So this definitely converges to 0. This definitely converges to 0 again. Here n is a natural number. Okay. Maybe greater than 0. Okay, both is fine. So if you take n is equal to 1, that is just the sequence 1 1 1 1 1. And if you take n is equal to something bigger, so just take n belongs to n. If you take n 2, then you will get 1 1 by 2, 1 by 2 square. So again it will converge to 0. This converges to 1. So, and this converges to 0. Here e raised to power 0, e raised to power 1, e raised to power 2. This is a sequence which does not converge. So if you want to prove that this does not converge to 0, you should be able to write the so for Cauchy sequence, what is the definition? For limit, what is the so for a Cauchy sequence, you should be able to prove that negation of Cauchy sequence, right? What is negation of Cauchy sequence? Uh, it says for every epsilon. So there exists some epsilon greater than 0 such that for every n belongs to n, a n plus m minus a n is greater than epsilon. So that is the negation. So for every will change to sum, and sum will change to for every. So that is kind of negation, if you understand. So there you ask for every epsilon, you should be able to find out some natural number which satisfies this less than property. Okay, here less than. Now you should be able to find out some epsilon which contradicts that property, that for some epsilon you will never find any natural number, like you will never find any natural number such that this will become less than. That means for every natural number you are able to for every natural number you should be able to get greater than epsilon. Okay, so just take epsilon to be 1. Okay, so I should be able to get epsilon, right? So I am choosing epsilon to be 1. Okay, so E is your 2.72 around. Okay, now right, so that is your sequence epsilon 0, epsilon 1, epsilon 2, like this is your sequence. Now I'm saying with this epsilon you will never this is always greater than epsilon. Let's see what is this value, and this and your regular n. So for every n, okay, and for every m, right, so okay, and just putting the values. What is this? E raised to, it is started with 0, so there is one replacement. Okay, so this is just n plus m minus 1, and this is n minus 1. This should be greater than 1, I'm saying. So n minus 1, and m belongs to n, right? So just take this difference and you have minus 1. So I'm saying this is greater than 1. We need to prove that. Okay, this is equal to now n is a natural number. Okay, right, and m is greater than 1, greater than or equal to 1, n is greater than or equal to 1. So just look at it, this value is what, 1 point at least. So this is greater than or equal to m, if m is equal to 1, that is the minimum value it could have. So this is 2.72 minus 1, that is 1.72, and n could be greater than or equal to 1. If it is 1, then it is just 1. If so this value is coming from n equals to 1 and m equals to 1. So this whole value will always be greater than this value. This implies this value, and that is what, that is greater than 1, because 1 into 1.72 is definitely greater than 1. So you have what now for this epsilon, whatever you choose n, you will always get greater than 1. So that is the proof for this is not convergent. Is that okay?
Yes.
Okay. So in your question, this is the task, and you for this also try to write it explicitly. That is a best way to do. Like you can see this convergence. Just try to write it in a form, in this form. So for every epsilon, you should be able to find out some capital N such that this property holds. Not this, less than or equal to. Okay. A complex number is an algebraic integer if it is a root of monic polynomial. So this is kind of a definition. A complex number is said to be algebraic integer if you can find out a monic polynomial. Monic means, as I said, the coefficient, leading coefficient is 1. That means if the highest degree is x raised to power n, and it's like this, some coefficients are there. For example, an x raised to power n plus an minus 1 x raised to power n minus 1. Let's say this is the leading coefficient. That means this is non-zero. So it is not like the highest degree term. The highest degree term has the coefficient equal to 1. That is monic polynomial. Okay. So a complex number is an algebraic integer if it is a root of such a polynomial. Okay. In zx, the coefficients are in z, in zx. Okay, which of the following are algebraic integer? Let's say if we have something, so you have first I. For I, which polynomial you can take? If you want to say this is
x square plus 1.
Exactly, very good. So if you take this, then the root of x square plus 1 is iota and minus iota. So you just need a polynomial such that which has root this, whatever has been asked. For root 2, what can you take?
X square minus 2.
Exactly. For iota root 2?
X square plus 2.
Exactly. Very good. So all of the above. So all are algebraic integers. Okay, let's move to the next question. Which one of the following maps is a possible homomorphism? So possible homomorphism, that means they are asking for, okay. Okay, so it is not written what exactly is. Just assume these as a group. Okay, groups, group homomorphism. We are talking about group homomorphism. Okay, so we have group homomorphism, ring homomorphism, field homomorphism. So it should be mentioned. So here we have group homomorphism. So F R to R. So what will you consider if it is not written? Definitely you are talking about addition because 0 is there. And you are saying group homomorphism. That means for multiplication 0 should not be there because 0 does not have inverse. Okay, so definitely they are talking about addition. Okay, so F is this map and Fx is equal to mod x. So for homomorphism, what should happen? You know, fx plus y should be equal to fx plus fy. That you need to check. So this is for homomorphism. Okay, so for homomorphism, this should happen. So let's check if this is happening. So let x and y belongs to real number. Then fx plus y is what? Mod x plus y, right? So mod is your positive value, like absolute value. If you have minus 1, then f of minus 1 is just 1. So this is like this. Okay, so it is just making it positive. If you want to write it in a form, if you know this, it is. So this is actually minus of minus x. Right, yes. So minus of minus x, so it makes it, am I writing right? No, sorry. So this is, right, exactly. So this is what? So if you want to write it in a form, so this is fx is equal to x if x is greater than or equal to 0, and this is minus x if x is less than 0. So that is the point. Okay, now what they have asked, so that is, and now if you take fx plus fy, what will you get? Mod x plus mod y. Are they equal? Are they equal?
True.
For example, yeah.
X is equal to 2 and y equal to minus 3.
Yeah, okay. Have I listened correctly? So let's take x to be 1. Exactly, I got your point, no doubt. So whatever you take, just take the minus 1 of it. Then this is just 0 mod, mod 0, that is just 0. And now other direction, this one plus this one will be just 1 plus 1, and that is 2. So that is not equal. And actually, if you know, this is always greater. Okay, greater than or equal to. Okay, so first one is not true. What about second one? Second is given to be r cross. Now whenever it says r cross, that is you are in multiplicative field, sorry, multiplicative group, because 0 is not here, so additive identity is not here. So cross, okay, you remember this, no? R cross represents r minus 0, so you just remove the 0 element. So that is your r cross. So this is the map f r cross to r cross. This is, and f of x is equal to sine of x. Now what you need to check? Now you have multiplication, right? So this is multiplicative. So fx, exactly. So what happens? You have, let's say, x star. So that is the property which should hold, right? So whatever operation they have, that is, these are the operations. Okay, in the homomorphism, what you need to, so we should write, these could be different if this and this are different. So okay, I'll write it. Let's say this is your group G1 comma star to G2 comma another operation. So what should happen? Fx star y of this operation, because x and y are elements of G1, this should be equal to f of x of like this operation f of y. This should happen. Now here what do you have? You have star and of to be, sorry, these are both multiplication, normal multiplication, real number multiplication. So f of x into y should be equal to fx into fy. That should happen. Okay, that is your question to prove. So let's check sine of x plus y. So this is equal to what? Sine of x plus y. Are they equal? Sine of x into sine of y, are they equal? That is your question, right? So can you see that are they equal or not?
No.
No. For example, just for example, we know that these are not equal, right? Even in my mind, can I find an example?
X equal to pi by 4 and y equal to 1.
And y equal to 1. So yeah, exactly, very good. So you have sine pi by 2 and you have here sine pi by 2 into sine 1, and sine 1 is definitely, so sine pi by 2 is just 1, and that means sine 1 is equal to 1. That is not equal, exactly. So these are not equal. Very good. How about the third one? Z to z fx is equal to x square. So again you have fz to z. So what will be the operation?
Addition.
Addition, exactly. So fx is equal to x square. So what you need to check, if you take x plus y, this should be equal to x square plus y square, right? Which is not true again. Just take 1 minus 1. That is again a problem. Okay, so this is a problem. What about the fourth one? Fz plus 2z2 plus fx is equal to 0 if x is even, else fx is equal to 1. So f is a map from z to z2. So z2 means mod 2 operation. So this is addition, and z2 plus 2. Plus 2 represent addition modulo 2. Mod 2. Okay, so this is your map. Now what has been asked? So again the map says fx is equal to 1 if x is even, else 0. So else, that means yeah, you could say odd, no doubt. So this is 0. So yeah, other way around, exactly, because 0 should go to 0, so 0 is even, so it should be like this. So here excuse me, fx plus y, this is addition, so that is equal to, if so, how will you check? You will take even and even. First take even, then take even odd, and take odd. These are the three options you could have. So if you take even, what will you get? This is fx. Yeah. So when you add even numbers, you will get 0. Right? This is even. Right. So this is even, this is even. When you add even number and odd number, then you will get 1.
Odd.
And with odd and odd, you will get
0.
yeah. So in here will you will get 1 plus 1, that is 0 in mod 2. That's why these are equal. So we are talking about the right side. Here it is right side. When you take even and even, you will get, yeah, exactly the same. You understood, I guess. Okay, so this is a homomorphism, group homomorphism. Okay. Let's move to the last question. Using Lagrange's theorem, we know that if the order of an element, so this is Lagrange's theorem standard, if the order of an element of a finite group is D, then D divides cardinality of G, which we used earlier also. So the converse of this statement is false in general. Okay, so in general definitely false. Okay, so do you know, okay, so for a finite group G, if that is what, if D divides order of G, then there exists an element in G of order, okay, that is misleading. So there exists an element of order D in G. So that is your statement. So that is a question. So in general it is not true. Do you know any example for this? So if some number divides order of G, and that is definitely finite group. So finite group means this cardinality makes sense. This is not infinite. So if D divides order of G, then there exists an element of order D in G. Do you have any example for which this is not true? Okay, just take right. So this is Z2 cross Z2. You understand that? So that is actually isomorphic to Klein 4 group. So just think of this Z2 cross Z2. What are the elements? Elements are 0, 0, 1, 0, 0, 1, and 1, 1, right? And what are the order of this element? Order of 0, 0 is just sorry, this is the identity. So this is the identity, so order is just 1. Okay, because we are in addition, these are with addition. Order of yeah, D makes sense. Order of 1, 0, what will be the order?
2.
You just add 2 times, you will get 2, 0, and that is 0, 0, exactly. How about this? This is also 2, and this last one, order
2.
Exactly. So you see all the elements have order 2. Now just take D to be 4. So the cardinality of this set is 4, right? Order of G is 4. So G is your Z2 cross Z2. Take D is equal to 4, and order of G is 4. So 4 divides order of G, but there is no element of order. There is no element of order 4. So this is not true in general. That is an example. So actually this is true for a prime number, which is a very standard theorem that is called as Cauchy's theorem for finite groups. That says, this theorem says, if or maybe for every prime number dividing order of G, let G be a finite group. Okay, this is for only finite groups. Even the name says, for every prime number dividing order of G, prime number P, dividing order of G, there exists an element of order P. Okay, so this is true for prime numbers, not true in general, as you saw the example. So this is definitely true. For every D smaller than 7, so definitely you have 4. This example, this is not true. D is an odd prime, so this is a subset of this case. So we'll take the most probable answer, that is this. And D is an odd number, so okay, so for 3 into 3 you will get an example definitely for 9, right? Which one I should take? Okay, so we are talking about D9, sorry, not D9. You have order of group to be 9. Oh, take this, that will be better. So do you remember this group 27 of this kind? 0, 0, 0, 0, 0, 0, 1, A, B, C. So the order, so this is Heisenberg group, if you remember. G is this, such that A, B, C belongs to Z3. You asked me some question earlier, so there I use this example. So this is Heisenberg group, and this is a non-commutative group. And what does that? So every element has order 3. So I use this example for to prove this. If this is true, then this does not imply G is commutative. I use this example for this case, and here this does not imply, and you can use this example because every element has order 3. So that means these are just identities. So this is definitely going to be equal for every ABC. Sorry, for every AB. But here this is not a commutative group. You multiply 2 elements, you will not get the both side, you will not get the same thing. Okay, so use this example. Here every element has order 3. Now take 9 or 27. There are no elements of this. 9 divides 27, even 27 divides 27, but there are no elements of order 9 or 27, and that will give the last option incorrect. Okay, is that okay? Okay, so this was the last question for today's class. So I'm done with my questions. You may ask your question.